how do we fit a line, how do we fit a model to that distribution? And so what's going to happen is we're going to create what we call the least squares regression line. And so the first part of this section, we're just going to talk about what the least squares regression line tells us, how are we able to use the least squares regression line, how to interpret the different parts of it, and then tomorrow we're going to talk about how to actually calculate it and use it as well. So when we talk about this linear model, it's an equation of a line, and when we look at that equation, what it's doing is it's modeling how the response variable y changes as the explanatory x changes. So as x changes in the problem, how does y also change? And so we're going to use kind of a modified slope-intercept form for our regression line. So this is the model that we're going to use, and I want you to make sure you write your answers in this form. This is what it's going to look like on the formula sheet that you get for the AP exam, which means it's going to be the form that's going to look like on the formula sheet you get for your tests. Okay, so you don't have to memorize this modified form. You do need to know what it represents. You need to know how to interpret the different parts of it. But that's what we're going to be looking at. So that y hat is equal to a plus bx is going to be our format. So y hat in this case, and that's what that notation is read as. So this little caret symbol up above, that's the predicted value of y. And it is important that you have that notation correct. When we use this linear model, we're not calculating y. We're not calculating the exact value for my response variable. We're calculating a predicted value. When we create our regression lines tomorrow, and when we look at the regression lines in today's examples, they're not going to pass perfectly through the data because the data doesn't perfectly line up. Okay, so when we're doing these predictions, we're going to try to get close to what the true value should be, but that's why we have a different notation for it. So that's kind of the first thing, is just making sure we understand that when we use that y hat, it's because it's a predicted value, not the actual value. The other parts of this then that are important to take note of, the a in this case is my y-intercept for the equation. That's where we're going to cross the y-axis. We're going to talk about interpreting that here in a second. And then b is the slope of my equation. And so understanding what the two different parts that go into this equation are, knowing how to interpret them, is what we're going to primarily focus on today. So we'll talk about how to calculate the y-intercept. We'll talk about how to calculate slope tomorrow. But for today, it's just understanding where they are in the equation and what they actually mean for the problem. So when we put all of that together, like we said, we're creating what's called that least squares regression line. And the whole purpose of this line is to allow us to predict values of y based on x. So we collected some values that have an x and a y coordinate associated with them, but we want to know what might happen at different values of x. And so we're going to use these regression lines for that prediction purpose. So an example here, so they went through and collected items from Burger King's menu. They measured the amount of protein in the item as well as the amount of fat in the item. So my explanatory variable they chose as protein in grams. The response variable they chose as fat in grams as well. And so what they did was they plotted the 30 or so menu items that they collected. Okay, so that's what that scatter plot on the right side's showing us. And then what they're also showing us is what the regression model, the linear model, would look like for this scenario. So if I were to calculate that regression line, we'll talk about how to do that tomorrow. That's what it's going to look like. And so what they start us off with is the actual equation. So here's my regression model for these Burger King menu items. Now when we write our equations, there's two different forms that you can use. There's that first one that I highlighted in orange there, and there's this second option that I'm going to highlight in purple. When they ask you to give the regression model, so when they actually ask you to calculate that regression model and report the values, you're going to write yours in this exact format. Now, if you choose this first method, so if you choose the y hat equals the a plus bx, okay, as soon as you state what the equation is, you then need to accompany it with what y stands for and what x stands for. So if I were doing this on a problem where I was coming up with the equation myself, after I write the equation, I would have to say y is the amount of fat and x is the amount of protein. So when we start to write our regression models, if I'm going to use the x and the y notation, then I have to define x and y as well. The other option is to just put the variables in the equation already. So instead of saying y hat, we can say the amount of fat or predicted amount of fat, right, with the notation. We have our y-intercept and our slope, and then x is representing the amount of protein. So I can just replace x and y with what they represent directly. So if I use that first option in orange, I have to define x and y. If I use that option in purple, then I already have defined x and y. I don't have to do anything additional. So when you guys write your equations, you're free to use either format. Just understand that the one requires a little bit more work. And then like we talked about, for these regression lines, the whole purpose is for us to be able to predict values that we don't have access to. So in this case, the question might be, given this regression model, if you want to consume 25 grams of protein for lunch, how much fat should you expect to consume? So if I was going to use that regression model to predict, I want to predict the amount of fat by using the equation and plugging in the value we're asking about. So they gave me the amount of protein. That was my x variable. So I plug in the 25 grams for protein. I would then plug this in my calculator. And I believe if you work this out, you get about 31.07 grams. So part of the homework today, that's all you're going to be doing. They're going to give you a regression model. They're going to give you the background on the information, and they're just going to ask you to do predictions. So based on this model, what do we predict the value of y would be for this particular value of x? So plug in your value of x, put it in your calculator, get your approximate value. Everyone okay with the format and plugging in for prediction? Okay. The next thing then, when we deal with our slope and our y-intercept, so understanding what those numbers represent is going to be really important as well. I guarantee on the test that we take for this unit, on the quiz we're going to take on Thursday, they're going to ask you to interpret the values. So you need to know how to interpret the slope primarily. You need to know how to interpret the y-intercept, okay? And so when we do this, our regression line slope is always expressed in units of y per units of x. So that slope is telling us how y changes in relation to x. So for the example that we just looked at, that slope of 0.97 means the predicted amount of fat increases by 0.97 grams for each additional gram of protein in an item. So what I just highlighted in blue there, if I asked you to interpret that value, that's what I would want to see. So when we're thinking about slope, you need to have a statement that more or less says something to the effect that for every additional value of x, so each additional unit of x, whatever that happens to be measured in, y increases or decreases by this amount. So every time we interpret that, it's about how y is changing based on x. Okay, so that's an important part of this, making sure we know how to interpret that. For each additional unit of x, y, or the predicted amount of y, or the predicted value for y will increase or decrease by this amount. And the increase, decrease obviously changes based on the sign. If I have a positive association, then y is going to increase as x increases. If I have a negative association, I'll have a negative slope, so y will decrease as x increases. The other thing of note here, when we talked about correlation last week, we said that changing units doesn't affect correlation, doesn't change the strength of the association, but regression lines aren't the same though. When we look at regression lines, the units are still attached to everything. So if I were to take my grams for x and convert those to kilograms, that's going to change everything involving my regression model. So units don't affect correlation because we strip the units from the correlation value. But if I'm looking at slope, I'm looking at y-intercept, I'm looking at my overall graph, changing the units will absolutely change everything else about it. When we look at the y-intercept then, that's the value that we would predict for y when x takes on the value of 0. So in our Burger King example, I think the y-intercept was 6.82. So if we were to interpret that, we would say if a menu item had 0 grams of protein, we would predict 6.82 grams of fat to be in that item. So it's just whenever x, whatever that happens to be, a 0, this is what we think y would be. Now, as far as prediction purposes go, the y-intercept is not extremely useful because x equals 0 is not typically a plausible value for x in a real-world scenario. So as far as the interpretations go, they may ask you about that interpreting. As far as prediction, it's not going to be very useful to us because that x value equal to 0 doesn't usually take place. So it's really just a starting point for our line, and that's kind of the entire purpose for it. So of the two of those, interpreting slope's probably going to be the more important one. So making sure we know how to do that. Extrapolation then is the next thing. So when we use our lines for prediction, we do have to be careful when plugging values of x into our regression model. So when we look at our scatter plots, we have created that scatter plot, we've created a regression model based on the values we've already collected. Okay, so we have a specific range of values for x, we have a specific range of values for y that were associated with the scenario we're looking at. What happens with extrapolation is when we are trying to predict values that are beyond our given range of values. And so what we have to be aware of is if they ask us to extrapolate, the results cannot be guaranteed to be accurate because we have no idea what happens outside of the scope of what we looked at. So an example of that would be age versus height. If I took a kid and every year I measured their height and I tracked their height progression, and let's say we did it from age 8 to age 14. So if I track their height progression, that's usually a pretty linear association. If I tried to use that model that I create to predict how tall that kid's going to be when he's 45, what's going to happen? Yeah, I'm going to predict that he's a giant, right? Because what happens with height versus age? Yeah, eventually you stop growing and in fact you start shrinking instead, okay? So eventually that kid's going to stop growing at that rate, which means I can't use my model to predict outside of the scope that I'm looking at because I'm not probably going to get accurate results, right? And so that's the whole point, is we know what is happening for the x values we've collected. We have no idea what happens outside of that. So even in our Burger King example, if I go back to that for a second, So based on what we collected, I know what typically happens for any menu item that has between 0 and 50 grams of protein. But if they ask me to predict what amount of fat would be in an item if there were 60 grams of protein, we don't know what would happen there. Maybe the model continues, maybe it doesn't. Maybe it levels off, maybe it changes direction. So when they ask you to extrapolate, we cannot put any level of confidence in that guess because we have no idea what happens outside of the scope that we looked at. We know what the pattern looks like for us. Outside of that could be anything. So we try to avoid extrapolating whenever possible. So then the next thing, when we use this model for prediction purposes, we talked about the fact that when we plug in a value of x, we're calculating a predicted value of y. Well, so what we want to know sometimes is how accurate is our model. So how close do we actually get to the actual values that we collected when using this model to predict? And that's what a residual is. So a residual is the difference between the actual value that we collected and what the model would predict for that value of x. So in essence, it tells us how far off the model is from the true value at that point. And the way we create our residual model, it's kind of like when we calculate our mean and standard deviation, okay? When we calculate that regression model, it should go more or less directly through the middle of my scatter plot, which means I should overestimate and underestimate about the same throughout the entire graph. So when I calculate all of the residuals, if I add them all together, I should get a total sum of 0. Because I should underestimate in some instances, overestimate in others, and because of the way I create the model, it should do so equally. And so when we calculate residuals, we use that equation that you see up there. So the residual is the actual value. So this is my actual value for y. Versus my predicted value. And so in the graph, it's trying to give you a visual representation of that. If I were to look at this menu item right here. So I have the amount of protein and the amount of fat for that particular item. So I know the actual value for x and the actual value for y. If we're interested in how close the line is at that point, we could plug that value of x into our regression line, and it's going to predict the amount of fat that should be in that item. And so what we're seeing here is the actual value of y for that item was here, where we plotted it. My regression line, though, predicted it to be a little bit higher. So my line overestimated the amount of fat that would be in an item at that level. So when I calculate the residual, I'd be calculating the difference. How far off was the model at that point? The other thing here that's important to note, residuals are sometimes denoted with the lowercase e. So when they ask about residuals, sometimes they use the notation, the lowercase e, to denote a residual. So that's just something to kind of be aware of. When we talk about residual standard deviation tomorrow, they use that lowercase e to represent that residual. But that's what we're talking about with residuals. It's for that particular value that we collected, how close was the line to getting that correct value of y. Okay. When we calculate these residuals then, part of calculating these residuals is also interpreting what they mean. So when I calculate that residual, since I'm taking the actual value minus the predicted value, and that's important to remember that direction. Actual minus predicted. A negative residual means that the value that I predicted was too high. When I subtract and my second number is bigger than my first, I get a negative result. So a negative residual represents an overestimate on the part of the regression line. So it guessed too high. And then the value of that residual was how high they guessed. So how much more they predicted than what actually happened. And then on the flip side of that, if I get a positive residual, it means that the predicted value was lower than what we observed. And so in that instance, it underestimated the true value. So the sign of the residual immediately tells us whether we over or underestimated, so knowing which one represents which. And then the value itself tells us how much we overestimated or how much we underestimated in that scenario. So as an example, so the stats for the relationship between the average number of points scored per game and the number of wins for the 12 college football teams in the SEC, as well as a scatter plot with the least squares regression line, residual plot are shown below. Now, this has way more information than we currently need. So for instance, we're going to talk about this graph tomorrow. So right now, there's nothing that we need to know about that. We're going to talk about residual standard deviation, R squared. All of that's coming tomorrow. Okay, so for right now, the only thing we're concerned with is we've got that scatter plot on the left. We've got a regression line where they gave us the equation for it. Those are the things we're focusing on right now. So based on this regression line, if I wanted to interpret the y-intercept here, so x was the number of points scored per game, y was the number of wins that team would have, okay? So if I wanted to interpret this y-intercept, we'd say if a team scored 0 points, okay, so if I had 0 points scored every game, I would win negative 3.75 games. So this is an example where that y-intercept really is not beneficial to us in terms of prediction purposes because that doesn't even make sense. Okay? So in that instance, that's probably one that they would not ask you to interpret. But the slope absolutely is applicable here. So what they're saying is with that slope of 0.437, it says for each additional point that a team scores per game, they can expect, or we would predict, that they would win 0.437 more games. So each additional point you score, the number of wins you have increases by 0.437 games. So when we interpret that slope, that's what we're always looking at is when x changes by this amount, what happens to y? Okay. With this then, we can also look at residuals. So it says calculate and interpret the residual for South Carolina. They scored 30.1 points per game. They had 11 wins on the season. So they highlighted that point on the graph here. So this would be South Carolina's results. Okay. When we use the line to predict how many games they should have won, we plug the 30.1 points per game in for x. We find that the predicted number of wins was 9.4 wins. So when we take the actual number of wins minus the predicted number of wins, we see that South Carolina won 1.6 more games than expected based on how many points they scored. So this is what the interpretations for a residual would look like. So based on the result that we get, we got this much higher than expected or this much lower than expected based on my value of x. So in this case, we underestimated the number of wins. They actually won more than we predicted. If this had come out negative, that means that they didn't win as many as we thought they would have. So we would have overestimated in that scenario. Okay. So, this is the assignment that you were supposed to start looking at on Friday. Hopefully, if you were confused on this one, because I did run into a couple of kids over the weekend and they were talking about how confused they were. So hopefully now this makes a little bit more sense as you look through those problems.